Good morning, afternoon, evening, night, whenever you're watching this. This is day 6 for EE 488. I am Ward Jewell, your instructor. Today we're back in the workshop to continue our work on real and reactive power, and specifically on power factor. You can see in the webcam the drill press set up with the metering equipment. Let's take a look at that. Just a quick review. The drill press is over on the left side. I'll try to point things out to you. So here's the drill press. The drill press 120 volt cord is here. This goes to the drill press from this outlet strip. The outlet strip is supplied through the watt meter. The current to this outlet strip is going through the watt meter through a current shunt resistor, a very low resistor, converts it to voltage. That's what displays in the voltage display on the watt meter. The watt meter itself is connected to a 120 volt outlet through this 120 volt cord. So the watt meter is displaying on the left real power, on the right either voltage or current. And a very short time into the recording, I don't actually have a time shown on my recording, but I had to pause and see why the current is not reading 0, because it should be very close to 0. It's reading 0.99. The reason is I have something else plugged into this, and we'll be talking about that in a little while. So I'm going to turn that other something off and see the current go down to 0. That's the setup we've been working with. We did originally using the two digital multimeters to read voltage and current, and the oscilloscope to get phase angle. Last time we used the oscilloscope to get voltage and current magnitude and phase angle, calculated real and reactive power from those. We'll start with the values that we got on day 5. So these are data from day 5. Write that word in here. This was measured data. Using the oscilloscope, we got a value of voltage, a phasor, 120.2 volts. We called that the reference, so we gave that an angle of 0. We also measured, using the oscilloscope, current to the drill press, 2.1 amps at an angle of minus 32 degrees. That was from the oscilloscope. We verified the magnitudes using the watt meter. I never verified the phase angle. And we calculated complex power, vector S, complex power, real plus J times the reactive power. Units are volt amperes when we are talking about complex power. Units on power are watts. Units on reactive power are volt amperes reactive. So we can say, oh, I didn't give you the value. This equals 216. I'll put the units in here, plus J, 135 VARs. Those are the values. So from that we can say real power is 216 watts, reactive power 135 VARs. We can also put a magnitude on this, so the magnitude of S, which we call apparent power, is equal to, it's the magnitude of that vector, so we can do a calculation if we need to. 216 squared plus 135 squared, square root of that, Units will be volt amperes because we're in apparent power. I'm trying to keep things straight here. 255 volt amperes. Now, we talked about how reactive power is something that we calculate to represent increased losses in the power supply system that brings the electric power to the customers, to the users. We use reactive power to represent that. It isn't the losses. It's not a physical quantity, but it is proportional to the losses. As reactive power increases, losses increase. That's about all you can say. You could write an equation. It would be extremely complex. So, instead of using reactive power, because reactive power varies for this drill press, the reactive power it's consuming at no load is 135 VARs. For a large drill press in an industrial setting, the reactive power and the real power would be significantly higher because they're larger devices that can do more work than the one I have here. The reactive power here in my house for the air conditioning compressor would be significantly higher than 135 VARs because it has a much larger motor in it. So in general, reactive power depends on the size of the load and how many loads you have that are using reactive power. So it's not a great value to give to indicate what the losses are. A better value to give is a ratio, and the ratio is what we call power factor, and it's abbreviated PF for reasons that should be obvious. There are several ways to calculate power factor, but the correct way, the way that always works, is to take real power in watts and divide by apparent power in volt amperes. There's another way we'll calculate it in just a moment that you're probably more familiar with, but this is called true power factor because when you get into non-sinusoidal situations, this is the one that works. So in this case, 216 watts divided by 255 volt amperes gives us a power factor of 0.85. Ratio of real power to apparent power. Now we have a ratio that gives us a better idea of the quality of this load in terms of reactive power. We have to put a word on this to signify whether the load is inductive or capacitive. Most loads on the power system are inductive. Something like 70% of electric energy that is generated goes to induction motors. And induction motors have power factors between 0.7, 0.8, and this one is actually a little bit high, 0.85. I believe that's because this is a very inefficient motor, very inefficient device. Remember, it's running unloaded. There's no bit in the drill press. It's not drilling anything. The 216 watts of real power that it is consuming is losses. So because it's a fairly inefficient machine, I think that real power that it's consuming as losses actually brings the power factor up. The reason we need to know whether it is inductive or capacitive is because we're going to correct the power factor. We correct the power factor on the power system. We correct the power factor within facilities in order to reduce the amount of current that's flowing, reduce losses, and also reduce voltage drop. So this one we measured with an oscilloscope, and we saw that voltage leads current. In this case, current was lagging, so let's rewrite that. Current lags voltage. We measured that. We didn't have to know what the load was. Lags is the power factor. Power factor refers to the current angle relative to the voltage angle. So whatever current does, if it leads, it's a leading power factor. If it lags, it's a lagging power factor. For this machine, because it's an induction motor, I could be fairly certain that it's lagging. However, I tested several single-phase induction motors that I have around my home. The rest were all fans, and they had power factors right around 1, which I was surprised to see because induction motor power factors are usually pretty low, 0.7, 0.75. My guess is that the manufacturers put capacitors across the motor to improve the power factor, but I don't know. And the only way I could find out is to take one of them apart and look for a capacitor. And I think I would see those capacitors connected, but I don't know. And that's an extra expense for the manufacturer, and they don't tend to do that. But I tested several, and they all had power factors right around 1. I know they're small induction motors. They're inefficient. So the point of all that discussion is just because it is an induction motor does not mean it's lagging. There was once when I was in an industrial facility, and I was there because they were confused about their power factor. And they thought they had a 0.9 power factor. And they thought it was 0.9 lagging, which was a reasonable thing to think because they had lots of induction motors. It turned out it was 0.9 leading, and when they tried to correct the power factor, it reduced it because it reduced it leading. I'll show you this. I'll give you a demonstration of this. So our power factor is 0.85 lagging. The other way we can calculate it, if we have a single frequency sinusoid, which is all we're going to do in this class, but it's not all we do in reality. And if you have a distorted waveform, this can give you significant error. Power factor is cosine theta, or cosine of the angle on the voltage minus the angle on the current. Remember, in the oscilloscope image of the current was not sinusoidal. And that, again, is because it's an inefficient induction motor. It's heading towards saturation. But we assumed it was a pure sine wave, and so all our calculations are going to match here. So if we do cosine, angle on the voltage, minus angle on the current, we get the same power factor, 0.85, and we know that the voltage is leading, so we can call it lagging power factor. That's power factor. Again, the reason we use it is because it is an indication of how inductive a load is, usually how inductive, but how much that load is increasing losses and possibly how much it is causing a voltage drop on the system because of increased current. So, because reactive power increases current, increases losses, reduces voltage, we correct power factor. So, we correct power factor what was our model of that induction motor? We had a nice model of it. Just a resistor in series with an inductor. And there's the source. I'm not going to do any calculations from this, but that was our induction motor. Actually, it was our drill press model. Let's be specific. I didn't measure just the motor. That's the only thing I had turned on there. There is a little light you can turn on, but still, this is the drill press model. So to correct, it's inductive. So to correct inductance, you can put a capacitor in there, and you can do it two ways. You can put one in series, so you could put a capacitor here, or you can put it in shunt here. And we put it in shunt. It's more convenient, usually, to connect something in shunt, to connect something across the load, because you don't have to disconnect anything. If I wanted to connect a capacitor in series with that drill press, I would have to remove some connections and get it connected in series. So I don't want to do that. It's easier to connect it in shunt. Also, if you connect it in series, it reduces the impedance of this whole thing. And if you get a short circuit, it increases short circuit currents. So that's a downside of using series capacitors. So we use shunt capacitors. So right there, shunt capacitor. So if I want to correct power factor to 1.0, which we also refer to as correct power factor to unity, we need a capacitor that will provide 135 VARs. So we need a shunt capacitor. Let's write this out. Provide 135 VARs at 120 volts. What capacitor is that? We can calculate the current in the capacitor. IC 135 VARs over voltage 120.2. Okay, now you're thinking, hang on, you told us we have to always do complex math when we do calculations like this, and that is correct. So why can I do this scalar calculation? I'm going to write it down, 1.12 amps, because Q, as we know, magnitude voltage, magnitude current. In this case, current through the capacitor, cosine, angle voltage minus angle capacitor current. All right. This is 1. That's why I can use the equation above. That's not a minus sign. How do I know that's 1? In a capacitor, ice, I leads E. E is an archaic term for voltage, but you can remember Eli the Iceman to remember which leads, voltage or current, in a capacitor or an inductor. So current leads voltage by 90 degrees. So angle on voltage minus angle on current is, if we call the angle on voltage 0, and we call the angle on current 90. And yes, I have an error, and now my computer is falling apart, probably because of that. Minus 90 degrees. And here's my error right here. Just going to point it out to you, and I'm going to correct it. Q is not VI cosine theta. Q is VI sine theta. I am sorry about that. Some of you were wondering about that from the moment I wrote it. And I was doing the math in my head and saying cosine of minus 90 is 0. It's not 1. So now sine of minus 90 is, sine of minus 90 is minus 1. So I said this was 1. It's minus 1. So using just this part of the equation will give me the current magnitude through the capacitor. If you have questions about that, just let me know. The voltage across the capacitor is 120.2. The reactance of the capacitor, XC, similarly, we can leave the phase angles out of this because it's the voltage magnitude over the current magnitude, only because the phase angle is 90 degrees. So when I do that, I get 120.2 volts divided by 1.12 amps. And that gives me a value in ohms of 107 ohms. Knowing that that is 107 ohms, I can calculate capacitance, which is 1 over omega times the reactance, 1 over, in this case, we calculated using the period that we read from the oscilloscope, 370 radians per second times 107 ohms. And when I do that, I get a value of 25 microfarads. That will correct the power factor to unity. Let's see if that really works. I have connected in the circuit the other thing that was turned on when I was not getting a zero current. This variable capacitor. The capacitor, I'm showing it here so that you can see, here's the plug, and because I'm connecting this in parallel with the drill press, I just plug that plug into the same outlet strip here that is supplying power to the drill press. Here's the cord plugged into the shunt capacitor, and then I can switch on whatever capacitance I want within the range of the 5 capacitors that it has. I can combine capacitors in parallel, but I don't have it's not infinitely variable. It's not an infinitely variable capacitor. So this is what I have to work with. Notice how these are marked. This one says 240 ohms. So that's reactance at 60 hertz, somewhere on here, and it was blocked by the cord. It is blocked by the cord, but right down here, there's some other specifications, and it's given as 120 volts, 60 hertz. So the X is 240 ohms at 60 hertz. 0.5 amps is the rating. Don't put any more than 0.5 amps, but that's what flows through that capacitor at 120 volts, 60 hertz, and 11 microfarads. So I said I need 25 microfarads. There's 22. I drew over it. There's 22, 120 ohms. I said I needed 107 ohms, 22 microfarads. So the closest one I have is this one. So I'm going to connect it. I'm going to energize everything, and we're going to see what that does for us.